Hi everybody, welcome back to another video on Feynman integration. Today we'll be evaluating this integral, the integral from 0 to pi over 2 of the arctangent of sine x over sine x dx. We'll be evaluating it using the Leibniz rule. And our first step is to create a function of t closely resembling our original integral. And that's right here. You see I just put a t right in front of that sine x. The next step is to use the Leibniz rule to take a derivative with respect to t of the function by simply taking the derivative with respect, a partial derivative with respect to t of the integrand right there. And what you get if you do that is this, and I'll leave it all to you to verify that. Next step is to make the substitution that u is equal to tangent x, represented by this triangle up here. If you make that substitution, you will find that dx is equal to 1 over u squared plus 1 du, and that the sine of x is equal to u over the square root of u squared plus 1. And you can see that up here. And then you plug in the substitution and do some algebra and stuff like that, and you arrive at this, that f prime of t is equal to the integral from 0 to infinity of 1 over u squared times u squared plus 1, then that plus 1 du. Next step is to make another substitution, and there obviously must be a more direct substitution, since, if you make one substitution and then make another substitution, it's really the same as making one substitution. So it could be done. I wasn't able to see it. This is how I did it in my notes, so this is how I'm showing it. But anyway, the next substitution is that tangent theta is equal to u times the square root of t squared plus 1. And that is represented by this triangle right here. Using that substitution, you will be able to arrive at this. That is f prime of t is equal to the integral from 0 to pi over 2 of 1 over the square root of t squared plus 1 d theta. I was pulling my hair out at this step. I knew it should work and it wasn't, and the reason was that I was trying to, I wasn't, this is a constant. This is just a constant. So it's just going to be, basically bring this outside the integral, and it's the integral from 0 to pi over 2 d theta times 1 over the square root of t squared plus 1. Yeah, that was kind of a beginner's mistake on my part, but I did it. Anyway, so this is our f prime of t. It's just pi over 2 times the square root of t squared plus 1. Then we make yet, Now, since we have a good expression for f prime of t not involving integrals or anything, it's right here. What we want to do is go back to f of t. So we integrate this with respect to t, and that is represented right here. We'll have f of t is equal to pi over 2 times the indefinite integral of 1 over the square root of t squared plus 1 dt. And then I made another substitution. Actually, this is a different integral, so it doesn't count as another substitution. Anyway, the substitution is tangent theta being equal to t. And you can, tangent phi being equal to t. This is phi, not theta. Since I already used theta, you don't want to get confusing. I know phi and theta look awfully similar. But anyway, yeah, so tangent phi is equal to t right there, t1. And that secant squared phi d phi is equal to dt. And so what you do when you apply that substitution is you get that f of t is equal to pi over 2 times the indefinite integral of secant theta d theta. The indefinite integral of secant theta d theta is one you're I believe required to memorize in a lot of calculus courses. It is the natural log of secant theta plus tangent theta. But anyway, that's right here. We just have f of t is equal to pi over 2 times the natural log of secant theta, which is this part right here. You can see, I keep saying theta, it's phi. Secant phi, which is right here, secant being the hypotenuse over adjacent, secant phi, plus tangent phi, right there, tangent phi. and then plus c. And that c can be easily found to be 0 by using the fact that our f of 0 is equal to 0. So we will have 0 is equal to, well, this whole part will evaluate to 0, because if you plug in 0 for our t, you'll just end up with the natural log of 1, which is 0. So we'll have 0 is equal to 0 plus c, or c is equal to 0. So there's our final definition, our final result for f of t. And to get the value for our original integral, all we do is plug in 1, because f of 1 is equal to I. So we have that integral up there is equal to I, which in turn is equal to pi over 2 times the natural log of the square root of 2, which is right there, plus 1. So that's it. It's equal to pi over 2 times the natural log of 1 plus the square root of 2. And that's it. Hope you enjoyed that.